Hi everyone, welcome to the second part of my video on causal graph, backdoor, front-door criteria, and do calculus. In part one, if you haven't watched it, please go ahead and watch that. It's super, super important. I talk about causal graph. I talk about confounder. I talk about backdoor path. And I talk about do operator and etc. What we are trying to look at in the language of causal inference as well, which is super important. I will recap that. This part two, which is this part, we're gonna talk about two of the most important theorem that Judy and Pearl discussed, which is the backdoor and front door criterion. Backdoor and front door criterion. All right, it's very, very important. A lot of your questions that you have in industry can be solved by this too, by backdoor and front door criterion. So it's very important to have a good grasp on that. All right, in the first part of the my videos that I explained to you that what we are looking for in causal inference. All we are looking to answer in causal inference is this. We are trying to answer what's the probability of achieving Y, given that we have an intervention, we make an intervention on treatment X. Y is the outcome. I will write it down. I explained it also in part one. Please go ahead and watch part one. Probability of achieving outcome Y given intervention or treatment X. That's all we are trying to answer. However, it turns out it's not as simple as the randomized controlled trial because we have a concept of confounder. So all this massage, all this gymnastic that we do with this equation is just to get an answer that is not based on the do operator and also can take care of the confounders, in fact, actually in place, right? Because we have a backdoor, unwanted path. And I explained about this in part one of this video. Now, all right, so now that's what we are looking for. I also talk about the ladder of causation and what this operator mean actually. From your probability classes, you know what P of Y given X. This means the probability of achieving Y seeing X. This is the conditional probability. This is what you're trying to estimate in a supervised learning problem. That's a classic or discriminative model, right? So Judy Appel called this one curve fitting. So this is the first step in ladder of causation. This is called seeing. What we are talking about is P of do X. This is intervention. But these two are different. Unless you're in RCT, randomized control trial, means that there is no confounder. And step three is a counterfactual, which we are not going to talk about this. So P of Y given X, in general, is different from P of Y to X. All right? So the goal of causal inference is to start with this one and then come up with do-free expression at the end. All right, based on all the observed parameters that we have. All right, great. So that was a recap. Now that we're talking about the backdoor and front door criterion, so what we are trying to do is that let me just show you this graph, X and Y. So we are trying to find the probability of Y do X. All right, but you have this confounder Z. If there was a randomized control trial, this confounder Z wouldn't exist. There wouldn't be a confounder there. And that would be pretty easy, right? So this do X become X. Now, we have to find a way to condition on this Z, block the path. We need to find this, in part one, I explain about this unwanted path, backdoor path. We need to get rid of this, control for that, block it, however you want to. I'm just using different terminology just to make sure that when you're reading different book, you're really familiar with that. All right. So for that, Judy Pearl proposed backdoor criterion. So we say Z set of variables Z satisfy in backdoor criterion if two conditions are valid. If one, which is very, very, very important, this one, no, in a sense, Z is not really ancestor of the X. No node is Z is ancestor and descendant of X. I will explain about this. And two, which is very, very important, Z set of variables. Here is just only one variable. It can be ZW. I will give you an example. Z blocks, this is the most important one, blocks all backdoor from X to Y. This is one of the, perhaps the most important thing. This is the important condition that you need to understand. All right. And now that we understand this, let's take a look at what this condition means. So the first one said no, the first one is very obvious. It said no node in Z is a descendant of X. Means that Z is not child of X, none of the nodes that exist. For example, this is one of the example. It can be this as well. Just want to make sure that this can be Z, it can be W, right? So this condition, these two are for example, call it Z, right? So this set becomes Z and W. They are the one in the backdoor path. All right, let's take a look at this. So what this one says is that this Z should not be descendant, means that it cannot be child, means that the arrow from X cannot go to this variable. They can be parent of X. In the part one, I explained about this. It cannot be child of that. Of course, why? So you don't need to memorize anything. Why? Let's see, let's consider this one. Let's consider this one W. Let's consider we have Z here, and then we have Y here. Means if you have a Z here, this is a directed path. This is a direct path. This is a causal path. We don't want to block this. If we block this one, we get the causal impact of 0. If we block this one, we block the backdoor path. This is a causal path. This is a wanted path, right? So that's obvious. Of course, we don't want no node in Z to be descendant of X. But the second one is very important. The second one is very important. We want to make sure that the Z blocks all the backdoor path, all the unwanted path. We want to make sure that Z blocks every path but the direct path, but the causal path, right? So if I give you an example here, we have Z1, we have X, we have Y, we have this, and then we have Z2, we have this, right? If we have this one, so let's say that we want to find the set of variables Z that satisfy the backdoor criterion. It would be what? It would be Z1 and Z2. Why? Because if you go this route, this is one backdoor. This one is going to be another backdoor. Z should block all the backdoor path. All right? Okay. If this is the case, and we have these variables such as Z1 and Z2, let me copy this one here. We want to go back. But the same thing applies. Copy here. We want to find the expression for this. Great. Let me delete this. Let me delete this. All right. In this graph, this is just one example of that. We are trying to find this. How can we do this? We are trying to do this. There are many ways you can find this expression. Guys, I want to find the expression. Remember what we are trying to do. I've seen some posts in the internet. The number of posts about causal graph is very limited about the do operator. And the reason is that because I have a feeling that majority of people do not really know this stuff. That's one thing. The second thing is I think majority of people memorize this stuff. I have a feeling that honestly, that either of these two conditions are valid. People come up with advanced equations. They use do calculus. Of course, you can derive this from do calculus, which is a part 3. Where I'm going to talk about that. But why do I derive this from do calculus when it's such an easy question? In epidemiology, this got a standardized equation, adjustment formula, a standardized formula, right? So let me just give you one way to derive this one, easy way to derive this one. There are many ways to think about this one. Many ways to think about this one. All right, guys, so if I want to find the do x, what's going to be the graph? the modified graph. Remember, this is G. In the part 1 of the video, I told you that we have called G X bar. Means that go ahead and when you apply do operator, you're gonna go and remove all the edge from the parent to the variable X. So you have Z, the edge from Z to X will be deleted because I'm making intervention. I'm setting the value myself. I don't want the parent determine the value. X, Y. Great. So I have this. This is gonna be modified graph after I make the intervention. All right. Good. Let's take a look at this one. Guys, I'm gonna remind you the law of probability, law of total probability. So if you have a P of Y given X in this condition, in this, let's say in this graph G, how would you calculate this one? You say that Z, P of Y given X and Z, right? And it's P of Z given X. That's one way to calculate it, right? If you add just a probability, let's say it's a probability class. It's not a causal inference. It's not a lecture on causal inference, it's a probability class. That's how you would calculate it, right? Probability of Y given X and Z times the probability of Z given X. And sum over Z. But now that we have this do operator, let's do the same thing. Z probability of Y given do X, Z probability Z do X. Okay, good, great, fantastic here. All right, so let's see what I've done here. I just assigned this one as a do X, and then all I've done is just replace X with do X here. I said I'm trying to calculate this quantity. All right, let's take a look at this graph now. Let's take a look at this graph. Guys, based on this graph, what do you see here? If I go ahead and find this modified graph, there is no confounder here, right? Do and seeing is the same. Z, that there is no edge from Z to X. So do of X and C of X are the same. This is a graph of RCT, this one. This is like a graph of RCT. So on this one become P of X and Z, right? But what's going to happen to this? What's the probability of Z given do X? Because Z and X, what's going to happen? Z and X are independent, right? Because Y is a collider. Z and X are independent of each other. Y is a collider. Y close the backdoor path from here to here. This path is closed because Y is a collider. So probability of Z given do X is just probability of Z. And this is a backdoor equation. This is a backdoor formula, right? As simple as that. You can derive it using do calculus. Perhaps I do it as an example in the next video. I derive this for you as in a do calculus. But do you have to do that? That is a very simple derivation. Again, so remember, if you condition on collider, you open the backdoor path. If you don't condition on collider, the path is already closed. And what's the structure of collider? This is a collider. X1, X2, X3. Here, X3 is a collider. Means both of them collide. There is a collision in X3, both of them. And this one, this path, by default, is closed. So X1 is independent of X2 here. X1 is. Now, this one, X0 is not independent of X2 condition on X3 because once you condition on collider, the path is open, right? So that's called the backdoor criterion or backdoor equation, backdoor formula. That's it, as simple as it. That was a backdoor formula. All right, now this is the most important, I think, condition that you need to remember in the most important formula in causal inference, because the majority of the problem can be solved with this. But now we have another case here. And I derive this one using do calculus for you as well. There are many ways to derive this. There are other ways to derive this as well. But I derive this one using do calculus as well in the third part. Now let's talk about the frontal. And then you will see that why I go over backdoor first. Because frontal criterion is nothing but two backdoor criterion applied back to back to each other. So frontal criterion is just a result of two backdoor criterion. You will see it's very easy. But what's the setup for the front door criterion? If you have a graph like this, z, x, I'm not going to call it z, there is a reason. I'm going to call it u, and then m, and then y. Right, so what's the setup here? U is an unmeasured confounder, unmeasured, unobserved. Oh, you don't have a value for the U, confounder, but perhaps is there. You see how important is that? X is treatment, M is mediator, what we call mediator. So M is a variable that exists on a causal path, on a direct causal path. M is a mediator. X is a treatment, and Y is the outcome. All right, what are we trying to do? Like always, we are trying to find the Y given do X. Can I do the backdoor criterion? Absolutely. If U was measured. In the backdoor criterion, there was no notion of unmeasured confounder. Remember? You see, guys, this path is not closed. Why? Because I don't know you. I cannot condition on you. You cannot condition on you. So the backdoor criterion is not applied. So I'm trying to find a way to find the P of Y given do X. Unbiased estimate, of course, right? Because of course you can just calculate the path from X to Y, and then that will give you the bias estimate. I'm trying to find the unbiased estimate of that. And this will lead us to the front door criterion. So let's say what's the front door criterion? What's the front door condition? You remember what's a backdoor condition? There was a set of things that had to be valid for a backdoor condition, right? For a front door condition, also there are a set of things that has to be valid, set of rules that has to be valid for the backdoor condition for a front door. Let's see. Set of following conditions must be met in order apply the front door criterion. And these are very, very intuitive based on the graph that I have. What's number one? Let me change the color here. Number one. Okay, this is the same color. Number one. M, the mediator M. Or I will put it like this. All causal path from X to Y should fully be captured by M. It means that all the causal path from X to Y should actually go through the M. This is very, very important. If this is not actually met, then you cannot really apply this. That's actually the first condition. All the causal path from X to M should actually fully be captured by the what should pass through the variable M. Two. All the backdoor path from M to Y should be closed by treatment by X. Is this correct here or not? This is a backdoor from M to Y. It's closed if we condition by X. We can close it, right? If you condition on X, you can close all the backdoor. You can close all the backdoor path if you condition on X. All right. So the path of MX, let's say UY, I don't care. U is okay. U is an unmeasured confounder. But if you condition on X, that path is closed. Is a D separator. Okay. And the third one, which is a very, very, very important one, is that there is no unblocked path. There is no unblocked backdoor path. I will say backdoor. from X to Y. It's very important. There is no unblocked backdoor path from X to Y. All right. So all the backdoor path from X to Y, there is no unblocked. And here we don't have an unblocked backdoor path. It's very, very important, this condition to understand in order to use actually these ideas. So all the backdoor path from M to Y should be closed by X, and they are closed. And there is no unblocked. It's very important. There is no unblocked backdoor path from X to Y. So all these three conditions and all the path from the causal path from X to Y should be mediated through M. Right? There are different ways you can say that. I say that mediated through M. You can say that all the path from X to Y should pass actually through the M. That's another way of saying this. If all these conditions are satisfied, then you can use the front-door criterion. So what's the front-door criterion? What does it say? The front-door criterion says that you're trying to calculate the 2 of X on this graph. All I'm going to do, let me just draw it again for you guys. This is very easy. All I'm trying to do is that there is a Z, there is an X, there is an M, and there is a this, this, and this. I'll call it U. Okay, so P of Y given to X. Guys, what is this equal to? Let's break it to a step. A step one. I want to find the impact of X on M. Let's find the impact of this on this. To find the impact of M to Y. This. A step three, combine. Is that correct? Because I don't have U, so I can't talk about U. So all I'm trying to do is just find the impact of X on M and M to Y, and then combine them together. That's all I'm looking for, right? Guys, this U always is present. Judy Appert himself said that you can always imagine that we have an unobserved confounder. There is nothing I can do about U. If you find the final expression and it's based on U, your final expression is wrong because we don't have the value. It's not identifiable. So, okay. So that's, okay. Let's see. Guys, what's the impact of X on Y? How do you show that one? P of M given to X. What's the P of M given to X? It's easy, right? P of M given to X. You see, guys, if you look at this backdoor from X to M, this one, it's blocked by Y, right? Y is a collider. So all the backdoor path is closed. What does it mean? It means, what does it mean? It means that causation and correlation are the same. There is no confounder. It means that P of M given to X become P of M given X. Super easy. Great. What's the impact of M to Y? Impact of M to Y. Y given to M. All right, so guys, what's the impact of M to Y? There is a backdoor path here. I see this. There is a backdoor path here from here to here. Is that correct? The path of MX, we don't know, and Y. MX. But remember the front door criterion? What does it say? All the backdoor paths from M to Y, all the backdoor path from M to Y should be closed by X. Means X should be able to block that. So I think we are good here. Isn't this front just a backdoor criterion? MXY. Let me just draw it for you. This is M, this is X, this is Y. I don't have U. I cannot do anything for you. So just apply the backdoor criterion here, right? Now I condition on, I want a condition on X. It's just a backdoor criterion. What's going to happen here? Here, Y given M and X, a probability of M, and then sum over M should be good. Isn't this the case? Just trying to actually see if isn't this the case? Okay. So now that we have this one, and this is actually pretty good, you see it, so it's just x is the, yeah. So now the final expression, when you're trying to find the probability of y given to x, the final expression doesn't have m in it. So you need to sum over the all value of m. So here, by the way, this should be p of x because x is a confounder. This sum over x. All right. So this is going to be sum over m, p of m given x, x, p of y given m and x, and p of x. Let me just tell you why I changed this one from m to x here. Because here, x is a confounder, right? Let me just write it better. X is a confounder here. It's very important. So remember over there was P of Z. I drive the backdoor criterion here. It was P of Z. Z was a confounder. So here M is a confounder. X is a confounder. And that's what you get. So now you see that people write bunch of equation, like long equation for front door criterion. No, this is a front door criterion. And we drive it as simple as that. You don't need to memorize it. All right. So remember, you need to have unmeasured confounder, and there are a couple of conditions that need to be satisfied. The path from x to y, very quick, should pass through them. All of them should pass through them. M should be mediated. M should be set of variables to mediate them. Like all the backdoor path from M to Y should be closed by X. And there is no unblocked backdoor path from X to Y. Right? So U is unobserved. But there is no unblocked backdoor path. So that's actually super, super important. This U, you can always assume it exists. You can never make sure that you can measure for all the confounders. So that U doesn't always exist. If U was observed, we just condition on it. It was a backdoor path that we had to condition on it. Right? We could close it. But here, there is no way we can close for that. All right? Because it exists, but we don't observe it. We don't, like, you don't even know it's present or not. So it's like a language of graph. We show it like this. All right. So we derive the backdoor and front door criterion, and we talk about the conditions of that. And we also talk a little bit about the language of the causal graph and also a language of the intervention versus actual seeing correlation. All right. So I will keep it for now for this video because it's gonna otherwise become very, very long video. In the next video, I'm gonna talk about do calculus, which is actually super important. And like always, if you like this video, please like and subscribe to the channel, share it with your friend, and write a comment if you have any question under this video, and I do my best to respond to your question. Thank you, and see you all in the next video. Bye.